All right, the topic for 1.4 is linear measure. We're going to start out with some vocab again, just like we did yesterday. And again, we are really going to emphasize the importance of notation today. So this column right here, this is going to be all about notation because that is super important for us. The first definition that we have here, we kind of touched on yesterday. It is a segment. We saw this in our homework. The difference between a line and a segment is that lines go on forever and ever in both directions, where segments have two endpoints. Okay, so they end somewhere. If you look in this diagram, you should see that I have a line drawn. I can tell that it's a line because of these arrows. So that means this guy goes on forever and ever in both directions. But on any line, you can make up a bunch of different segments between the points. So one segment here is PQ, the entire thing from P to Q. You have some smaller segments in there, for example, PM and MQ. Those are just some smaller pieces of the same line, right? Here's how we name segments. If lines use 2 points and then the line with the arrows on top, segments also can use 2 points and they get the line on top but no arrows. Sometimes they might get fancy on us and they might call them like segment QM. They might add in that word segment in the front. I don't know why they would do that, but sometimes they do. And what we're noticing when we name our segments like PQ and QM, the letters that we choose specifically are those endpoints. So we're always going to use those endpoints to name our segments. Questions on that? Okay, the next definition, congruent segments. Congruent is going to be a really big vocab word for us in geometry. When two things are congruent, it means they have the same measure or length. So in this diagram, we can see these two segments, AB and CD. Diagrams are going to be marked with tick marks to indicate that two things are congruent. So these purple lines here that I just drew in, those mean congruent segments. The way that we write that, if I wanted to say that these two segments were congruent, is I would say segment AB. My congruent symbol is an equal sign with a squiggle on top to segment CD. So right there, that's telling me that my two segments are congruent. Anytime we are talking about segments or saying that segments are congruent, again, we're noticing that line goes on top. One weird thing about geometry notation, however, is when we are talking about something's measure. So, for example, if I wanted to say the measure of AB is 1.7 centimeters, look what happens. All of a sudden, that line on the top goes away. If I'm using an equal sign, that's a kind of a rule of thumb to keep in mind, there's no line on the top. I don't know why they do that. They do that because they're picky. So again, if I were talking about the length of CD, why do I do that? Then it would be, again, no line on the top. Every other instance, though, it's got the line on the top. So if I'm talking about congruent, line on the top. If I'm referencing it in a sentence or describing it, line on the top. Okay, next one, distance between 2 points on a number line, the length of the segment that has those 2 points as its endpoint. So for example, if I am talking about the distance between B and E on this number line, I could literally go in and sit there and count all those different tick marks, or maybe something that works in your head, it's the absolute value of 2 minus -6. Right? That's how we figure out the distance. We take the one on the right, we subtract the one on the left. So the length of BE, or the distance between points B and E, would be 8. Again, notice because I'm talking about a length, I don't put that line on the top of my segment. Any questions there? The next one is midpoint of a segment on a number line. So again, we're talking about two different points. Let's refer to points B and E as my 2 points. The midpoint of segment BE is point D. We see it in here? By definition of a midpoint, the point that is halfway between the two endpoints of a segment, it divides the segment into two congruent segments. So we can add on a little note here. Because the midpoint of BE is D, therefore, these two halves that it splits it into must be congruent. So BD must be congruent to DE. Any questions on that definition? Now, we can't just go naming midpoints all willy-nilly. We have to have some kind of reason how we name midpoints, and that's like the opposite of what we just said. Because we know in this diagram that segment AB is congruent to segment BC, therefore, I know that B must be the midpoint. So kind of the opposite of what I just said. So let's say because AB is congruent to BC, or AB is congruent to BC, therefore, B is the midpoint of AC. Does that make sense? Sometimes we're able to just literally count up the pieces and see yeah, I can clearly see that this is 4 tick marks and that's 4 tick marks, so I know that must be the midpoint. Here, I can't just eyeball it, so I have to know that those two segments are congruent. Any questions on that? So midpoint is always going to be referring to a point. It's in the name, midpoint. But sometimes we have things that cut other things in half that are not points all the time. We call those segment bisectors. That word bisector literally means to cut into. Bisect, cut. So something that cuts something else in half is a bisector. This can be anything from a point, segment, ray, line, or even a plane. All of those things can be segment bisectors. A segment bisector passes through the midpoint and divides the segment into two congruent segments. So if I'm looking at this guy right here, I have the segment AB, and then I have this line K that goes through it. So I could say line K bisects, aka cuts in half, segment AB. Therefore, because we know that that's a bisector, oops, I'm moving things around. Therefore, hello. Those two pieces are congruent. We're going to get more into proofy language later on. You'll understand what that means. But this also works the same way backwards. If I know that AM and MB are congruent, then I can say that line K must be a bisector of that line. So maybe I'm going to draw a little arrow here that it works both ways. Now, what this does not tell me is it does not tell me anything about line K. All I know is that line K, those are like the scissors, right? They are the ones doing the cutting, but I don't know anything about that. So even though this diagram kind of looks like it's even, I can't say anything about this segment and this segment being congruent. Bisectors don't work both ways for both lines like that. Any questions on any of those definitions? All right, nice and easy. First example here, find xz. Assume the figure is not drawn to scale. We're never going to assume figures are drawn to scale in geometry. That's just a rule. So what's the length of xz? It's not rocket science here. I'm not trying to trick you. What's the length of xz? Yes.
6 inches.
Yeah, it's 6 inches. I take each piece, 4 inches plus 2 inches. To get that xz must be 6 inches. Now that in itself is easy enough, but then we start adding in variables, and that's where things can get a little hairy. So in number 2, it's the same idea. I want to find the value of x and the length of st. If t is between s and u, that does not mean that t is a midpoint. It just means it's in the middle somewhere. st is 7x. su, so the distance from s to u, is 45. And tu is 5x minus 3. So I've got all these pieces. How am I going to set up an equation that relates all 3 of these pieces? Kind of the same way that we just wrote that equation in number 1. Can anybody put it together? Do you have an idea? Anybody? Okay, so the way that we're going to relate these is that if I have 2 pieces, 4 inches and 2 inches, I can add them together to get the total, 6 inches. Same thing here. If I have 2 pieces, I can add them together to get my total. So my equation should look like 5x minus 3 plus 7x equals 45. It's taking that same format from that last problem. And from here, I'm just going to solve. So this is 12x minus 3 equals 45. 12x equals 48. And x equals 4. When we're solving these problems, just make sure that you're actually answering all the questions that it's asking. It does ask us to go back and find the length of st. So I'm just going to plug this in. Notice I'm using an equal sign, so my segment does not have a line on the top of it. st equals 7 times 4, aka 28. Any questions there? Okay, flip it over to the next page. In number 3, AB is congruent to BC. What does that tell me about AB and BC? What does that word congruent mean? Dahlia. They are equal to each other. So right off the bat, because I know that those 2 things are congruent, I should set them equal to each other. So I can say AB equals BC, and then I'm just going to plug in those values that they gave me. AB is 4x minus 2. BC is 3x plus 3. I subtract everything over, and I get x equals, oh, this is a 2. X equals 5. Again, we got to pay attention to our problem and actually answer the question that it's asking. So I have to go back and find the length of AB. I'm going to plug in AB equals 4 times 5 minus 2, or 18. Questions on this? Okay, next one. Now we're thinking midpoint. We're going to use that definition of midpoint. M is the midpoint of RT. So what does that tell me about these pieces on this diagram? If M is the midpoint. Yes, Caitlin. Yeah, they're congruent. First things first, I'm going to mark that on my picture. Remember, we mark things as being congruent with these little tick marks. So if they're congruent, just like we did in the last one, to set up this equation, we're going to set them equal to each other. 5x plus 9 equals 8x minus 36. Solve for x here. What do I get? 45 on the left side, 3x on the right side, x equals 15. And now to actually answer the question, I'm finding 3 different values, RM, MT, and RT. Let's start with RM. We plug it in. 5 times 15 is 75. 75 plus 9, 84. And now I don't want to sit here and have to do all that math 2 more times. So what's an easy way to know what MT is? It's what? They're equal. We know they're congruent. It's the midpoint. We said that in the beginning. So instead of doing any work, I know MT must be 84. If you do the work, it's a good way to check and make sure that you're right, because if you don't get the same answer, you know you did something wrong. What about RT? How do we figure that out easily? Nolan. Yeah, 84 times 2. Just double it. We know that there's 2 segments that are the same, so we can double that, and we get 168. Perfect. Any questions there? Let's keep trucking along. 2 more. This one gets a little bit weird. What is the measure of PR if Q is the midpoint of PR? So what do we know? Q is the midpoint of PR. What does that tell me about this diagram? What does that tell me about this diagram? If Q is the midpoint. Casper. Yeah, they're congruent. PQ is congruent to QR. What that also tells me is because they are congruent, whatever their measure is the same. So if QR is 6 minus 3x, PQ is also 6 minus 3x. So I'm filling in this diagram to help me out here. Now, do we see what our equation should look like when we set these up? What does it look like? I want to take 2 pieces, add them together to get the whole thing, right? So I can either do 6 minus 3x plus 6 minus 3x equals 14x plus 2, or maybe I want to save myself a little bit of writing. I know that there's 2 equal segments. So 2 of those 6 minus 3x's equals 14x plus 2. Do a little bit of solving here. I believe I get 10 equals 20x, or x equals 1/2. I'm finding what is the measure of PR. So I'm going to take PR, which is 14x plus 2, and plug in that 1/2. I believe I get 9. Any questions on that one? Okay, one more and then we're done, I promise. DE bisects AB at C. Some of these, I think it's best that we draw this out. So I have DE bisecting AB. That means DE is the one that is doing the cutting. AB is the one that is getting cut in half. So let's start with AB. Now I know that DE is going to cut right through the middle, like so. And that middle point is going to be C. Now by the definition of that bisect, what do I know about the segments in here? Anna? Yeah, which ones are congruent? Perfect. I don't know anything about DC and CE. All I know is that is the thing that I'm using to cut the other thing in half. But I do know that AC and CB are congruent. So now I can start filling in some values. I know AC is 3x squared. I know CB is 18x plus 21. And again, that word congruent should be telling me I'm going to set them equal. 3x squared equals 18x plus 21. Uh-oh, how do we solve this? Caitlin. Not square root the x. I got an x on the other side. Dahlia? I can divide by 3. What should I do first, though, Anna? We're going to factor it, which means we're going to move everything to one side, and then you're right, we are going to take out a GCF of 3. So let's move everything to one side first. Get it equal to 0. Anytime you see an x squared and an x in the same problem, you're probably thinking we need to factor. From here, I take out my 3 out of everything. And now I'm looking for factors. What are my factors of that x squared minus 6x minus 7? Oops. I know the factors of x squared are x and x. Factors of 7 are 1 and 7. I want a negative number that I'm multiplying to, so I know one's going to be positive, one's going to be negative, but I'm adding up to a negative 6. So my 7 must be negative, my 1 must be positive. By ZPP, I set each piece equal to 0 to get 2 answers. X equals negative 1 and x equals 7. Now, in algebra, we had you check your work, but we weren't really doing anything with it. In geometry, we definitely need to check our work, especially when there's 2 answers and one of them is negative. Because when we plug into a diagram like this, can the length of AC ever be a negative number? No, it doesn't make sense in geometry. So especially when we have those negative numbers and especially when we have multiple solutions, we're going to go in and check them. So I'm going to start with that x equals negative 1, and I'm just going to kind of do it in my head. 3 times negative 1 squared. Well, negative 1 squared cancels out that negative. I know that's going to be a positive number. 18 times negative 1, negative 18, plus 21. I'm in the positive. I'm good there. That one is okay. I check the other one just to be sure. I know 3 times 7 squared is going to be a positive. 18 times 7 plus 21, also going to be a positive. Both of those answers work this time. If one of them ended up not working and we got a negative answer, we would just cross it out, right? It's one of the solutions to our factoring, but it is not an answer to our actual problem. This time, they all worked out for us, though. Any questions on this? I'm going to make a little note. Check for negative lengths. Any questions?